Okay, well, yeah, I want to tell you about some things. Basically, I want to report on a paper that is completed, but that is pretty long, and so I'm only going to be able to do a piece of it. And then a sort of work in progress that actually I'm excited to talk about here because maybe many people in the room have things to say about it, perhaps. So anyways, the upshot though is that only going to be able to do a sampling of all the relevant mathematics. Only half an hour, so I'm told. Okay, so anyways, right. So to start, I want to just say some things about the subleading asymptotics of ECH capacities. Okay. Well, first, let me remind you, okay, so we have these CKs. These are these ECH capacities. Well, I think probably everyone in the room knows what they are, but just to be safe, let's imagine for the purposes of, well, in general, I have some symplectic form manifold. Then I have these numbers, capacities. They could possibly be infinite. The case that's going to be their capacities. So maybe the key property. I suppose I won't write it on the board because we have only a limited amount of board space, but these are supposed to be symplectic size measurements in the sense that if I can embed one manifold into another, each ECH capacity of the first is supposed to be no less than the ECH capacity of the, no more than the ECH capacity of the other. Maybe most importantly for our talk is the so-called Weil law. It holds in a lot of generality, but for our purposes, we mostly are interested in the case, say, where X is, say, bounded in R4. And then they satisfy the so-called Weil law, which says that the CK squared of X over K converges to twice the volume of X, where my notation for the volume of X is probably slightly strange. For me, the volume of X is just the integral of omega wedge omega over X. Some people might call this twice the volume of X because if you actually write out this form, it's going to be twice the normal volume measurement. But I like it this way. Anyways, this is the so-called Weil law. And what are the subleading asymptotics? So we're interested in.
So the grading of these things would be 2K.
Yeah, that's right. The grading is going to be 2K. Right, so the ECH capacities are defined using embedded contact homology. Yeah, please also, ask questions, especially if you don't know what I'm talking about. The ECH capacities are defined using embedded contact homology, which is this floor type theory. They're a sequence, so K here is just the sequence parameter. There's a first ECH capacity, a second ECH capacity, etc. Basically, a ECH capacity CK corresponds to a class in the embedded contact homology chain complex in grading 2K. And there's a contact Weil law relating the grading to the action of the class more generally. But for the purposes of this talk, we can just work with these capacities. Are there further questions? Okay, so anyways, this is so-called leading asymptotics, and the topic of the talk is the subleading asymptotics. So okay, what are the subleading asymptotics going to be? Well, so what we're interested in then is we define EK to be CK minus the square root of 2K times the volume. Okay. Right, so this is the discrepancy in the asymptotic formula, and what we'd like to know is something like what is something like the limit of the E sub case. Okay. Over here. Another question you might want to know is something along the lines of, are the E sub k's actually negative? Say for all k, or for sufficiently large k. And let me maybe just box these questions, because in some sense they're going to be motivating questions in my talk. And let me say a few words about each of them and stop if you have some questions. So why did I put limit in quotes? Well, it's not so clear that these should actually have a limit. In fact, it's not even so clear that they should, saying that they have a limit means that they should even be bounded, and it's not always so clear that they're actually bounded. So recently, Oliver Ettmeyer showed that, at least in this kind of setup where I have a bounded domain in R4, they actually are bounded, but it's still not clear they have a limit. But then I could look at the lim sup and the liminf and things like that. We'd like to try to understand. Hutchins has some conjectures about this as well, in terms of a Ruel invariant and the boundary. Not exactly relevant for this talk, but anyway.
It's a philosophy why that would be bounded in this case.
In the case of, yeah, right. So that's actually going to be related to sort of part B of my talk, but it has to do with symplectic packing. So what Oliver showed is, I'm imagining here that this is a smooth four manifold. The smoothness is important. So I have some subset of R4 bounded with smooth boundary. Yeah, I'm imagining this is a domain, so it's compact and everything like that. What Oliver showed is that this can be this has packing stability. So one way to say it is that it's fully filled by a sufficiently stretched ellipsoid. Basically, there is an argument that one can do along the lines of we know that ellipsoids have bounded subleading asymptotics. This thing is fully filled by an ellipsoid, so you get a good lower bound that way. Conversely, you can take the complement of this and put it in some big ball and fill the complement with an ellipsoid. That also follows from Oliver's results. And so you can get an upper bound that way. And so the subleading asymptotics of these E sub k's are quite related to symplectic packing. Later, I'm going to talk about some work with Richard Hind, at least if I have time. And Richard Hind and I also, independently, well, not even exactly independently. I mean, there's a close relationship between what Oliver was doing and what Richard Hind and I were doing, studying packing stability by way of these subleading asymptotics. And it's going to come up in my talk as well.
So, like, numerical question. Does your bound on E sub k get worse the skinnier the ellipsoid is?
Yeah. So generally what will happen is that if you have a very thin ellipsoid, the E sub k's will be very large. I mean, in absolute value. That can let me also get to question 2 here about the signs of the E sub k's. Also of interest to people in this room, I think, the way I would pitch it. So if you actually compute, almost any example for which we can compute things, what one finds is that in this limit, the CKs tend to lag below the volume a little bit. They're approaching this from below. So maybe the first computation people did were things like for balls and things like that. And you don't generally ever actually beat the volume bound. You miss it by a little bit. So one could ask whether that's a general phenomenon. To connect with Rohill's question, it says, for example, if you have one of these skinny ellipsoids, you miss by a fair amount and you miss, to the negative side. Now, the reason this might be of interest to additional interest is, for example, if you think about E1, the fact that this would be less than 0 is related to saying something about the systole of X. So in particular, if you actually have a domain of large systole, we might return to this later in the talk, you'll see that at least E1 has to be positive. Nevertheless, I don't think we actually know for these particular bounded domains in R4 whether EK for sufficiently high K actually has to be positive. And it's an interesting. Okay, so are there any questions about these questions? Okay. Well, so
is there a specific relation between the systole and the?
right. Well, the systole is going to bound C1 from below. So say you had a domain with very large systole. Like you could have a domain, or I suppose I should say a domain with large systolic ratio. You could have a domain, say, of volume equal to 1/2. Let's say we have a domain of volume equal to 1/2. And its shortest Rabe orbit could have action 1 billion. Okay. So then in this formula, C1 would have to be at least 1 billion because the systole bounds C1 from below. And this term here would just be 1. So in particular, if you have a domain with a very high systolic ratio, E1 is going to be positive. But I don't know much about any of the other EIs, especially this asymptotic question. And I guess just to link to some other ideas that I understand to be in the air from people in these rooms, one reason that I'm interested in this question is because I feel that there's perhaps a notion of curvature going on here, where this bounded domain in R4 is a particular kind of setup that possibly it should be forcing the EKs to tend to underestimate things. And it would be interesting in some kind of hyperbolic setting to try to understand if the EKs are actually overestimating the volume. And maybe people in this room know something about this. Okay. Are there further questions? Okay, so here's some questions that we want to understand, and generally these are hard questions that I would say we don't understand very well at all. But we can at least make some progress in some cases, especially the toric case. So again, some of you have probably seen this before, but if you haven't, I'm now going to introduce a quite interesting class of domains for which we actually can answer at least probably all of these questions. So I'm going to take a domain omega, in the first quadrant. And then I'm going to look at the subset x omega, which is going to be the set of Z1, Z2, such that pi norm Z1 squared, Z2 squared is in omega. So I'm thinking of this as a subset of C2, which I'm identifying with R4. I usually will assume, at least in this talk, that omega is convex. In which case you call it a convex toric. So just to give you an example, let's say I just have the triangle with, well, I'm just going to make it 1 and 1, then x omega is small. Okay, so there's actually a slight innovation here compared to what is often done. I mean, there's even some sort of rivalry, I'm told, where I have a notion of convex toric domain, and Michael Hutchings has a notion of convex toric domain, and mine is called Dan Vex, and his is called Michael Vex. But this is actually more general than all of them. Because I'm just saying I would take any convex set I want. It could be off the axes, it could touch the axes, etc. So if you're familiar with Michael Vex domains, they're a little bit more restricted. But anyways, we have these toric domains, and okay, so I wanted to compute the subleading asymptotic.
Convex is the ultimate convexity.
Well, this is actually the ultimate convexity. Yeah,
Convexity.
this is even more convex than Dan Vex. Yeah. So because both convex, Michael Vex, and Dan Vex were taken, I think we called these generalized convex toric domains. But this is the ultimate convexity. So anyways, okay, so the basic point is that we can answer these questions, at least for these things, and you get something interesting. So what do you get? So here's a theorem. We really have a small board, so I won't write the authors on the board, but this is a theorem of myself and Deuce McDuff and Nikki Magill. Says that if I look at the EKs of these x omegas, I can actually compute the limit. Well, it was known that the limit just doesn't exist. Even for a ball, I mean, later in the talk, we'll talk a little bit about how to do these computations, but even for a ball, the limit actually just doesn't exist of these E sub k's. So, but what we showed is that if you take the liminf of the E sub k's, you get negative the perimeter of omega over 2. Okay, now I have to tell you what the perimeter is. I'm going to put a little z here because it's not actually the normal perimeter for reasons that I'll explain in a moment. Let me just make a remark before I tell you what perimeter I'm using here. Call this thing star. Okay, so the remark is you can think of star as a two-term Weil law. In the toric case, And it's actually useful to compare it to the Laplacian. So these Weyl laws, they're called Weyl laws because they're inspired by Weyl's law for eigenvalues of the Laplace operator. Weyl proved the first term version in something like 1911. Then there's a conjecture called Weyl's conjecture, which I guess Peter Sarnak tells me he was embarrassed to put in print because he was worried that perhaps it was wrong. But anyways, Weyl's conjecture is about looking at the second order asymptotics in the Laplace spectrum and trying to recover the perimeter of the domain. There's a long history over the last century of works on that, with the conclusion that for some kind of domain like this in R to the D, if there are no billiard trajectories of positive measure, then Weyl's conjecture is true. Yeah. So here, well, we have no condition like that, and we actually do get the perimeter, although just for these particular four manifolds that are associated to these two-dimensional cases. But anyway, so this is like what you would expect from Weyl's conjecture, just in the toric sense. And I have to explain what this Z means, because this is not the usual perimeter. It's the Z perimeter.
So I thought this was like a theorem or Avery, right? Like
Yeah.
if there's zero measure billiard trajectories, then you have the two-term Weyl law.
That's right.
I thought that what was still open was whether this condition of having billiards of measure zero is actually generic or something.
Right.
Oh, okay.
Right. I mean, maybe I stated it in a slightly strange way. So there's a Weyl's conjecture, and then Avery proved it under the assumption that there are no billiard trajectories of positive measure. And then I think it's an open question whether you could actually have a billiard table like this.
But do you have an analog of that conjecture in your case? I guess like.
Well, it's an interesting thing to think about. Here we have the lim int.
This exact same question.
Yeah,
months ago.
it's a good question to think about. Here we have the lim int. And you definitely need the liminf here.
Yeah.
You're not, but of course, things like the ball, you actually do have a set of orbits of positive measure. So you could conjecture that the discrepancy between the liminf and the lim sup sees something about the measure of orbits on the boundary.
What would that look like in the toric case? Do you want like the set of like points with rational slope or something of the domain to measure zero or something like that?
Yeah, then you might expect that this is a liminf, and you might expect more generally that the liminf is a limit. And you might expect that more generally, there's a relationship between the difference between the lim sup and the liminf and the mass of the rational slope. Yeah, so I think that's very interesting. It seems plausible that one can make progress, but I don't know. Further questions? Well, I'm stopped. Okay, let me say what this pair Z is. Okay, so this perimeter is not the normal Euclidean perimeter. And if you haven't thought about these toric domains before, well, the first thing to convince yourself of is that it cannot possibly be the normal Euclidean perimeter because these toric domains are invariant under the action of SL2Z. And I could have maps of SL2Z that are doing strange things to the perimeter. So I really don't want the Euclidean perimeter. Instead, I want an affine invariant perimeter, and that's what this pair Z is. So this pair Z is the so-called affine perimeter. So it's basically the canonical perimeter that's preserved by affine transformations. Namely, what you can imagine is, say I want to say what the length of a tangent vector is. If I'm a vector, on the x-axis, I want to say that just has length, whatever its length is. But then I want to demand that this thing is actually invariant under the action of SL2Z. There's pretty much only one reasonable way to do it, and that's that affine perimeter. So just to give you some examples, if I look at this triangle that I looked at before, okay, this has perimeter equal to 3. Okay. Again, okay, so how do we see that it has perimeter equal to 3? Well, the way I was defining this perimeter, this thing has length 1, this has length 1, and now if I look at this line segment, of course, in Euclidean geometry, it has length √2. But what I'm saying is that it should be invariant under the action of SL2Z, and indeed I can find an affine transformation taking this to one of these friends. So that's why it has perimeter 3. On the other hand, if I take, say, this thing is 0, 1, this is 1 plus A, and this is 0, where A is irrational. This actually has length, this has length 2 plus A. So this has perimeter equal to 2 plus A. Which is another important thing to make sure you understand. So again, now my vertical line segment still has length 1. This one still has length 1 plus A. But because this thing is irrational, if I try to approximate it by rational things, if you work out the action of SL2T, you'll see that those are on the orbits of vectors that are getting smaller and smaller. So this actually has length 0. The diagonal has length 0. Okay, so that one doesn't contribute at all. In particular, what we learn from this is, and I guess I'll put a little, I don't know how do people draw like caution signs or something? So, I don't know. Anyways, I'll just put a little exclamation point here. So this perimeter is not continuous. Right, because I could imagine taking very small irrational numbers, that's going to be, the perimeter is going to be converging to 2, but that thing's going to be converging to this, this ball, which has perimeter 3. So it's a little bit strange, this perimeter, but it is the way it is. Okay, are there any questions about that? Okay. I'm going to erase things because there's not a lot of board space. So if I start to erase something that you wanted, just say, stop. Okay, so right, earlier even with Helmut's question, we discussed how these subleading asymptotics are quite related to symplectic packing. So you might wonder what kind of implications this has for packing, and it has some interesting applications.
Is there a way to provide this plan? Those formally.
Well, I can later in the talk I can give you a little bit of a formula for it, but it's not such an easy thing. Like okay, so maybe this is a useful thing to say. I mean, in general, maybe you'll like this. In general, say I have it, say some rational line segment. Say I just have some kind of polygon like this. Okay, so first of all, if you wanted a closed form for it, irrational things always contribute 0 to the perimeter by the same kind of argument that I was doing there. As for rational things, basically they contribute the number of lattice points on the segment -1, where what that means is that you want to scale it so that it will actually have a certain, like, you want to scale it so that as many as the ends, so that say like ideally you'd like to scale it so that all of the ends are at lattice points, and then you just count the number of lattice points on it, and that's a good way to do it. And you can almost do that. Maybe you can't quite do that, but you can come pretty close. And so basically the point is that for rational slopes, it's the number of lattice points in it, where you have to scale it so that it's actually has endpoints at lattice points, and for the irrational ones, it's 0. So for example, a circle, yeah, so if it's smooth, it's going to have perimeter equal to 0. So and that is going to be quite helpful when I start to discuss these applications to get a feel for this. So basically, irrational things and smooth things contribute 0 to the perimeter. Rational things contribute the number of lattice points on the segment, suitably interpreted.
There's some symplectic interpretation, like in terms of periodic orbits or something.
Yeah, I mean, it's possible you could give an interpretation along the lines of the discussion Rohil and I were having, is that when you have perimeter, it's often, but not always. It depends a little bit on the setup, but like a line of rational slope here contributes a positive mass of orbits. You have to be a little bit careful because in the S3 case, it can be a little bit more subtle. So I think the symplectic interpretation is actually a bit subtle. I mean, it's also a bit strange that it's evidently determined by the interior of the domain. So there's not such an easy answer. If the thing was completely off the axes, then the perimeter is closely related to the measure of the number of periodic orbits. If the thing is on the axes, it's a little bit harder to see, but then it relates to this conjecture of Hutchings that I mentioned at the beginning. I mean, Hutchings has his own parallel conjectures about recovering the Ruel invariant, which is something you can define using the flow from the subleading asymptotics of the ECH capacities. And presumably, one can relate the perimeter to the Ruel invariant, but I don't think anyone's actually done that. I mean, maybe in some special cases people have, but in this level of generality, I think anyone's actually related the perimeter to the Ruel invariant.
Yeah, I was wondering if you could write it as an integral of some kind of slope measure or something, right? Like, associated to the boundary of the domain, you can look at the slopes, and this gives you, I guess, this gives you some like measure on R2, roughly speaking. Or the measure tells you how much of the slope is concentrated at that particular point in R2. Yeah, and then you like just integrate with respect to that or something.
Yeah, I could believe that there's a formula like that. Yeah.
Actually, when it's completely out the axis, what does it look like? The Liouville vector field still goes out of the thing.
Well, yeah, it depends on where you want to, which primitive you pick, but you have to pick a point to define the Liouville vector field, and if you pick a point that's in the interior, then the Liouville vector field will still point outward.
Yeah, the reason I'm mentioning this way is that then the relation to the Ruel invariant becomes a little more transparent, because this thing I'm saying is probably exactly the Ruel density or something on the dynamics on the boundary.
I see.
Because I guess rational slopes lines of rational slope on the boundary correspond to like families of periodic tori, right?
Right.
With a fixed rotation number.
That's right.
So then I think, the Ruel rotation function on that family of periodic tori would give you exactly the rotation number or something.
I see. Yeah, that seems quite plausible. Something else that I would like to do is write it as an integral of some kind of curvature. At least in the closed case, there are parallel formulas where you can do that, but I don't know whether or not it's actually possible in the open case. Okay, well, let me actually state this application for you. So in the theory of symplectic embeddings, a very important notion is the notion of a full filling. So say this is a definition. Full filling of one symplectic manifold. The other is a symplectic embedding such that the volume of the domain and the target are equal. Volume x1 omega 1 is equal to the volume of x2. Omega 2, I won't write on the board what a symplectic embedding is, but it's just a smooth embedding pulling back the symplectic form, the target to the symplectic form on the domain. So for example, if I look at an ellipsoid, it's a rather famous result of McDuff and Schlenk, but this fully fills a ball this when A is at least 17/6 squares. So this is a rather famous result of McDuff and Schlenk. Yeah, so it's interesting because it's certainly not true for every A. For example, if you have an E1,2, you can only fill a smaller portion of the volume of the four ball. Okay, so this is the notion of a full filling, and we'd like to understand these better. In some sense, you particularly want to understand the full fillings because we're always interested in the difference between symplectic and volume preserving geometry. And if you have a full filling, then it means that from the point of view of these embedding problems, all the symplectic obstructions vanish, and you're just left with the volume preserving ones. And so in particular, if you have an obstruction to a full filling, then that means that there's something actually symplectic about the problem. So we're interested in obstructions. And so using our formula, you can get a nice one. Okay, so here's a theorem. So if the disjoint union fully fills some x, which I'm going to write as itself an x omega, then the perimeter, then the sum of the perimeters of gamma I is at least the sum, is at least the perimeter of gamma.
You say something would have equality with it. Is that a good question? Or not?
Yeah, actually, that is a very good question. Not so much related to what I'm going to be able to say today, but very related to my paper with Dusa and Nikki, because the case of equality is somehow very intimately tied to the theory of infinite staircases. That was another thing that we were interested in our paper. In this paper by McDuff and Schlenk, if you're not familiar with it, this is the behavior if the ellipsoid is stretched. If the ellipsoid is close to round, it's a very resonant thing where you get a staircase determined by the odd index Fibonacci numbers converging to the golden mean to the fourth. The golden mean to the fourth arises exactly via equality in this relationship here. And that was something we explored as part of a program to try to classify infinite staircases. But for time reasons, I won't be able to say much.
So if you have something with positive affine perimeter, then you can't be fully packed by balls, or
Yeah, almost,
I think I'm
but not
messing-
quite,
I'm
because
messing up the
remember,
lyrics.
right, so just to say, right, so the inequality is a little bit funny. It goes possibly in reverse to what you might expect.
Oh.
It's saying that in order to, if I fix my target, say, then in order to fully fill it, I have to accumulate enough perimeter. So what happens is if I have a ball as the target here, its perimeter is 3, and so it's telling you that you're not going to be able to fully fill it unless you've accumulated quite a lot of perimeter. But as we were discussing in the case of like a E1A, what happens is that as A gets very large, you actually do accumulate enough perimeter. Or if you let each of these be balls, basically as you take more and more balls, you're still going to be shrinking them a little bit if you're interested in packing stability, because you want the volumes to work out, but still the perimeter is going to eventually swamp whatever the target is here. As it should, because you actually do know that you have packing stability by balls. Right. Yeah, so it's a funny inequality here. But
I guess I was thinking if you choose omega so that the resulting toric domain doesn't have smooth boundary or something.
yeah, that's more like what we want to do. Exactly. That's more what we want to do in what I'm about to say. Right. Exactly. Are there further questions while I'm stopped? Okay, so you got this funny inequality on perimeters, which, as I say, is a little bit of like a reverse sort of inequality, because it's telling you need a lot of perimeter to fully fill something. And this in turn has implications for a question of Schlenk. Okay, so the following is a question of Schlenk. It's actually for any dimension, which is actually important when I get into the open questions. So we'll just let this be a domain, and we can talk about what exactly we mean by a domain in a little bit. So then the question is, if I look at the packing number of X omega, the question is this equal to 1 for sufficiently large K? Okay, so this is the case packing number by D. Let me tell you what PKD is.
It's a K, not a Y.
It's a K, yeah, sorry. I make it look a little more K-like. I've been told that my Ks themselves have a kind of fractal structure.
Then K looks like.
Exactly. So this PK D equals the proportion of the volume, the ratio, fraction of the volume volume of X that can be filled. Okay. Symplectically embedded. Big copies of my domain. Okay, so classically one usually thinks about the case where D is a ball, but Schlenk asks the question for a general domain. Similar questions were incidentally asked in a paper by Helmet and I think also Schlenk and Lachev and Seelybach. Anyways, just to make sure you understand the notation, you just take a domain in R2N, you take some fixed target, and you want to know what percentage of the volume can I fill with K copies of scaled versions of D.
They're all the same.
They're all the same. Yeah, I'll emphasize that they're rescaled by the same amount. And indeed, it is a different answer if you don't force them to be rescaled by the same amount. So if Schlenk's question had an affirmative answer, that would say that eventually, if I have many copies of my domain, I actually can fill 100% of the volume. Okay.
And what's the belief?
Well, I mean, in a minute, I'm about to say that it's wrong.
Okay.
Yeah. Right. And actually, the reason that it's wrong is along the lines of the discussion with Rohill now. So you get it at the corollary of double star, you can see that that's wrong. At least in dimension 4.
Eight copies have to be disjoint.
They have to be disjoint, but in some sense, you could imagine your domains are open and then it might make things a little bit nicer. But
it has it.
But yeah, they definitely have to be disjoint.
With the smoothness of the boundaries.
Well, right. No, yeah. So that's also kind of topical. So first, Richard Hind and I showed that this was wrong by taking X to have a very wild boundary. And then it's super wrong, like it fails for basically every domain. But also we want to use double star to show that this is actually wrong even for very nice X if I take D to have very small perimeter, along the lines of the discussion with Rohill.
Very small perimeter would mean
Like 0.
like smooth.
Could have smooth boundary, but 0 perimeter. So CG Hind proved no for X wild. That's not the topic of my talk, but actually one reason I didn't want to talk about it is that actually Richard gave a talk in the Symplectic Zoominar, which was videotaped, so you could watch Richard's talk if you're interested in that, and D at all reasonable. Let's say D has smooth boundary. Right. So in other words, I'm saying maybe 2 years ago or so, Richard and I showed that if X has a wild boundary and D has a reasonable boundary, like it's smooth, it doesn't have to be toric or anything like that, then the answer is no. But we were still wondering what if X is just normal. Okay, but this led to a question that we had, which is what about an X with non-wild X? I mean, so let's try to take the simplest possible X's you could imagine. Like we were interested in the case of a ball, or the case of CP2. I mean, I shouldn't speak for Richard. I was at least interested in these cases. What if you had a really simple X, not one with these weird boundaries? And then, well, then double star has a nice corollary about this. Okay, so double star implies that the answer is still no. Okay, so I can explain that actually quite easily.
So the machinery in dimension 4 is in that thing.
Exactly, yeah.
So-
We only have counterexamples to either of them in dimension 4. It would be interesting to find a counterexample in higher
We
dimension.
don't have machineries to talk about something like that or introduce
Yeah,
some.
not currently. I mean, right, exactly. So, but it's only in dimension 4 that we know this. So all of these are in n=2 case, i.e. R4. And yeah, so just to emphasize, especially if you're not used to thinking about this, this ECH is a special 4-dimensional theory, maybe dimension 3, dimension 2, but we don't know how to say much about it in dimension 6. And in particular, we still don't have examples in higher dimensions, and it would be interesting to.
So would it make sense to study the following question? Given any smooth domain in R2N, then is there a class of D can man say what should be true for D that it completely fills it?
Right. Yeah. I mean,
Is there, or is it
you could at least, right. So that might be in some sense a hard question, but at least this is giving an obstruction. So maybe I should spell out a little bit more why double star implies that the answer is still no. But you can.
I mean,
ultimately,
I think that the embedding question in all dimensions is really important. I mean, even if you don't know precisely in higher dimension what we're going to do with it, but
yeah,
but
no,
I think
completely
it's
agree.
like doing some kind of measure theory. You fully pack it, and you want to know what are the ingredients you need that you can do that.
I definitely endorse that message.
Wait, so I guess in the case of non-wild X, you
Like-
have to put some restrictions on D.
Yeah, for sure. Yeah, because if D is right, but Schlenk did ask this if this is always true. So to show that this is not always true, you just have to find a single D.
Oh, yeah.
And indeed, if X is not wild, it's certainly going to be true, for example, for ball, if D is a ball or something like that.
Oh, yeah. I was just wondering what the nature of this restriction is on D. Is it just like you can just say if anything with some perimeter or some restriction around perimeter?
Yeah, let me actually just write it on the board and then, yeah, exactly. So right. So but it'll just take a line, and I think that'll help. So what does double star have to say about this? It says we could take we can take D to be an X omega. Here's some X, here's some omega with perimeter of D equal to 0. And then in let's say X is in the B4 case, this means that the perimeter is equal to 3, as we saw before. Okay, so now you just stare at the inequality. The inequality is saying that in order for a fulfilling to exist, like if the packing number is going to be 1 for sufficiently large K, that means that I have to swamp the right-hand side here, which is going to be 3, by things coming from the perimeter. Well, I mean, you could have a lot of Ks. You could have like about a bajillion copies of D here, but it's not going to help if the perimeter is 0. So you get this basic obstruction coming from the perimeter. Let me just say, maybe more for the specialists, but it still works in the CP2 case, but it's actually kind of an interesting innovation, not especially due to me or anything, that it works in the CP2 case, because in the CP2 case, you have to use the theory of elementary ECH capacities. But it was a bit interesting to me because I don't know how to prove this with the ECH capacities, so only with the elementary ECH capacities.
What did you know for it?
Well, it's just, I actually don't know what the ECH capacities of CP2 are, but I do know the elementary ECH capacities of CP2. So to do the CP2 case, you have to prove the two-term Weil law for the elementary ECH capacities, which we also do. and then use the fact that you know what the elementary ECH capacities of CP2 are. But I don't know what the ECH capacity is. And you also have to define the perimeter of CP2, which is why I was mumbling about integrals of curvature.
What's
things like that.
What's
But
the issue with figuring out the ECH capacities of CP2? Maybe this is too far afield, but
no, I'm happy to answer it. I mean, I'm sort of burning time here, but let me answer it and then, well, the ECH capacities are most naturally defined for Liouville domains. And this is not a Liouville domain. So to understand the ECH capacities of this, I would have to know the supremum over all the Liouville domains that could possibly be embedded into CP2. And I don't have a good understanding of that.
But don't you have like you have an almost cofinal sequence of Liouville domains. You can fill everything up except for the for infinity, right?
Right. But it's the soup. So
yeah. Oh, okay.
You have to, I don't know, for example, whether if I have a reasonable Liouville domain, I can move it off the divisor or something. But you can get the elementary ECH capacities, and you can also show that it has a Weyl law, and you can make sense of this perimeter. Anyways, so this fails. I have, I guess, 5 minutes left. So let me just say then. I guess I don't have much time to talk about the proof. So instead I wanted to, there will be question and answer. You can ask during the question and answer. But instead I want to say this most recent thing, because I said I wanted to get people's thoughts anyways, about symplectic tiling, because it relates to this. So, okay, so we did this. So the question was still no. And so then we asked the following question, and earlier I said that I'm not sure Richard was interested in it, but this other question, I actually was able to get my co-authors to write it as a question in the paper. So they're at least somewhat obligated to be interested in it. So then we were interested in, okay, we know that this isn't one for sufficiently large K, but a natural question you could ask is the limit at least one? Let's say the lim soup. Well, let's just make it the limit. Doesn't point out reasons I can explain. Okay, so just to make sure people understand the question, Felix was asking, do these stabilize for sufficiently large K at 1? And then we showed that the answer is no. Then you could ask, okay, so they're not going to literally be 1. They might be 0.9, 0.95, etc. But can I at least show that maybe their limit is actually 1? And for example, McDuff, it's an old observation of McDuff and Polterovich that the answer is actually yes when D is a ball. So if you're doing packing by balls in any dimension, the answer is 1. But anyways, this theorem that I was saying that's work in progress, I mean, the theorem, the proof is definitely true. There's just other aspects of it that are works in progress. But we show a number of things, but we show that pk of D, the lim of pk of D of the ball is strictly less than 1 if the systolic ratio of D is at least 2.
Okay.
So maybe I'll pause for a moment because, like I said, I want people's thoughts at some point. But there's a region that we don't understand, which is what happens when the systolic ratio is between 2 and 1. Let me see the time here. Okay, I have 2 minutes. Let me state actually a slightly stronger version of this, and then I'll stop and you can ask questions that could even be like.
Is the capacities and
Shortest period.
Right, the systolic ratio. So I won't write it on the board for time reasons, but again, you can ask during the question and answer. So the systole is the length of the shortest Rabe orbit on the boundary. The systolic ratio is the square of the shortest orbit divided by the volume. So if the systolic ratio is at least 2, then the packing numbers actually say strictly less than 1. And you can think about this from the point of view of symplectic tiling, because when you think about it this way, we're thinking of the target as fixed and putting more and more small copies of our domain. But if you rescale in the limit, basically what you're saying is that I can't fill all of R4 by tilings of copies of D, if you reverse it. So this is saying that you can't tile R4 by copies of D. Anyways, let me just say, so in fact, what we show, getting back to this, I wanted to connect to that original question of the sign of EK. What we show is if the limit of the packing numbers of the 4-ball, I'll even make it a little bit stronger. If the lim sup is 1, then the EKs of D are all negative. So we give some interesting examples. So in other words, you could turn this around and try to ask a structural question about the ECH capacities. Remember at the beginning I was saying, are the ECH capacities always approaching the volume from below? And well, I said that obviously not, because you could have a domain with large systole. But what this is saying is that, okay, those domains with large systole don't tile all of R4. If you do have a domain that does tile all of R4, then it does have to be true that the ECH capacities are approaching from below. And so in particular, then, anytime you have a tiling of R4 by some domains, you learn some kind of generalized systolic inequality for all the ECH capacities. So, for example, we construct tilings by any monotone toric domain. So it follows from this that any monotone toric domain always has the ECH capacities. Converging from below. But this range of the systole from 1 to 2 is very mysterious to us, and so we're very happy to understand more about that. For example, like there are convex domains.
that is in convex domains, that would be this big squeezing between walls.
Right. So, for example, there are convex domains with systolic ratio greater than 1, famously constructed by people in the audience, and we don't know whether or not those tile.
So the normalization here is that the ball is historic ratio 1.
Yeah. That's sort of why I had my volume a little weird.
So it's
Okay. So, anyways, I think
So-
I'll stop.
So this counterexample for Mahler is a little bit, but that would be
That one would be in this
One
range.
point, so, but
That one would
how
be in this
far are
range.
we, did we go to two, only to 1.04 or something?
1.04. Okay. So we don't know whether it tiles or not.
But it's only for convex domains, right? For like not toric convex.
For
Convex
toric
domains.
convex domains, it should all be fine. I mean, you should, I mean, so what I was saying for the monotone toric domains, for monotone toric domains, they actually do tile. That's something we show. They do tile. A general convex toric domain actually still don't. I'm not sure.
Sorry, they do tile by this or by something else?
No, it's a non-trivial. We have to actually construct the tile. But I'm saying if you give me a monotone toric domain, we do construct a tiling of R4 for a monotone toric domain. But that's a little bit different than a convex toric domain.
Okay, well, I guess the question and answer session already started, but let's thank Dan for his talk. Now we can resume the question and answer session for everybody.
So for systolic ratio less than 1, do you know the opposite, or why is it drifting between from the?
Well, no, I don't exactly know what happens for the systolic ratio less than 1 either. But it's just we found this obstruction. We found this obstruction to tiling coming from the systolic ratio, and then we'd like to understand why we're getting the 2 rather than the 1. I mean, like, let me put it this way. You could look at the minimum systolic ratio such that you have a tiling of R4 by things of that systolic ratio, right? And this is saying that that number is at least 2. On the other hand, that number is definitely not less than 1 because the ball does tile R4. And so we're interested in the minimum systolic ratio. So it's not quite that if I have some domain of very small systolic ratio, I do know that it tiles, but I know that the systolic ratio gives an obstruction to tiling. And I know that if the systolic ratio is less than or equal to 1, I can at least find, I could find for any systolic ratio less than 1, a tiling by something with that systolic ratio. And I know that if it's more than 2, I can't do it. But I don't know what happens.
So is there an analog of this in the Riemannian case? I mean, I would bet in the Riemannian case, if you take some shape with weird curved boundary, you can't tile another domain in the plane. But I was wondering if there's something more.
Yeah, that's interesting. I mean, no, so these are actually inspired by, in the Riemannian case, you can study the so-called packing densities by D. People, you know, maybe it's most studied in the case where D is a convex domain. And then the funny thing is there's actually a conjecture due to a famous person, although I'm not sure that the person actually made the conjecture, if it was just attributed to them. I'm trying to remember who it is. But anyway, some famous person has their name affixed to a conjecture, possibly without their assent, that says that in the Riemannian case, if you're doing packing, it should be the worst possible thing to pack should be a ball in the set of convex domains. And then people compute often the packing densities of the ball, some of which are not known. But you know, some of these are quite famous, like you know, in dimension 2, the packing density of the ball is like this honeycomb lattice, and you can compute it. You know, in general, it goes down with the dimension. The conjecture is in the class of convex domains, the ball is actually the hardest thing to pack. So that's actually interesting because if the same conjecture was true in the symplectic case, I mean, you actually can fully tile space with the ball. So it would say that at least in the class of convex domains, this number is actually always 1. And I don't have a single counterexample of the class of convex domains. But for example, Pazit's example, you know, where the systolic ratio is greater than 1 is, you know, comes from this sort of pentagon, and then you can study, you can just look at what's the packing density of the pentagon in R2, and it also is somewhat related to the systole, although I think Richard didn't succeed in convincing me that it was like closely related to the systole, but it possibly related to the systole.
Cool. Let's thank Dan again.